Hi everyone, today a video in the Kinetics series looking at rate equations and rate laws. So the rate of a chemical reaction depends on the concentration of some or all of the species involved in the reaction. And this could be the reactants we have, it could also be catalysts. But however, they don't necessarily all make the same contribution to the rate of reaction. It could be that some of our species affect the rate very much, other species actually have no effect on the rate of reaction. Now there's something called the rate expression, and this tells us about the contribution of species that do affect the reaction rate. Now the detail about how each species contributes to the rate of reaction can only be found by experiment. We can't predict it, we can't do any kind of theoretical things in order to find it out. We have to do experiments to be able to find out how each species contributes to the rate of reaction. Now there could be a species that doesn't appear in the chemical equation that does affect the rate, and typically this might be a catalyst. Typically we show a catalyst kind of above a reaction arrow. It's not actually within the chemical equation, but catalysts can still affect the rate of a reaction. And so the key thing is that this rate expression is determined through experiment only. And it's an equation that describes how the rate of reaction at a given temperature depends on the concentration of species involved. Now, one of the key things there is a given temperature, because of course remember that temperature also affects rate of reaction. Typically, if I increase temperature, I get an increased rate of reaction. And we saw in the previous video why an increase in temperature leads to an increase in the rate of reaction. Now, if a species doesn't affect the rate of reaction, it's not present in the rate expression, but it will still be present in the chemical equation. So the chemical equation essentially shows us the species that are involved. The only thing typically we might not show in there is the catalyst, but even then we still show the catalyst over the reaction arrow. Our rate expression, however, may not include everything in the chemical equation. It may include things that aren't in the chemical equation, like catalysts. It's only stuff that affects the rate of reaction that appears in the rate expression. So let's take an example reaction of A plus B versus C plus D. The rate expression for this might look like that the rate of reaction is proportional to the concentration of A and the concentration of B. And so this would mean, for example, that both A and B have equal effects on the rate. If I double A, that would double the rate. If I double B, that would double the rate. If I doubled both A and B, well, this would now quadruple the rate. Essentially, you can imagine times by 2 and times by 2. Overall, that's timesing by 4, quadrupling the rate. Another rate law might be that the rate is proportional to A squared B. So the concentration of A squared, concentration of B. Now, what this means is that if I double B, the same thing happened as before. That would double the rate. Imagine times by 2 in there, times by 2 on the rate. But if I now double A, this quadruples the rate. And the way that I think about this, if I'm doubling A, I can imagine that inside the A brackets I have times 2. 2 squared is 4. And so actually we quadruple the rate. So we have to be careful with what the concentrations are raised to in terms of the power. Now, by introducing a constant into the expression, the proportionality sign can be removed. So we can go from being a rate is proportional to a rate is equal to. And this allows us to get something called the rate constant. The rate constant is different for every reaction, and it varies with temperature, because obviously the rate of reaction varies with temperature. And so that our rate law, for example, in that second example, would become that the rate is equal to K A squared B. So let's imagine that the rate expression is that what we just said. Rate is equal to K, concentration of A squared, concentration of B. This means that the concentration of A, which is raised to the power of 2, has double the effect on the rate of reaction than B does. And we saw that. If we doubled the concentration of B, we had double the rate. If we doubled the concentration of A, it would quadruple the rate, because we have times 2 squared, essentially. Now, the order of reaction with respect to a particular species is the power to which the concentration is raised to. It tells you how the rate depends on the concentration of that species. So for the rate expression that we have above, the order of reaction with respect to B is 1, because essentially B is raised to the power 1, but we don't show that if it's the power 1. And A, we would say, is raised to the power 2. Now, the overall order of a reaction is the sum of the individual orders. So because 1 plus 2 equals 3, the overall order of this reaction is 3. So the key takeaway is that if I have a rate expression with the form K, A to the power M, B to the power N, then the individual orders are M and N with respect to the concentration of A and B respectively, and the overall order is M plus N. Now, the rate expression tells us about the species that affect the rate. And as we said, not everything may affect the rate, and so species that appear in the chemical equation may not appear in the rate equation. Now, the coefficient in the chemical equation, that's, for example, if I have 2A plus 3B going to 4C plus D, that coefficient, the stoichiometric coefficient, essentially almost the mole ratio, has no relevance in the rate expression. So it's very different to an equilibrium expression. If you remember the equilibrium expressions, for example, Kc, we do our concentration of products on the top, concentration of reactants on the bottom, and we raise those concentrations to whatever the stoichiometric coefficient is. So if it was 2a plus 3b, we'd have to write that as a squared b cubed in our equilibrium expression. This is not the case for rate laws and rate expressions. The stoichiometric coefficients have no relevance on the rate expression. So in the example where we had it right at the top, where we have K A squared B, that doesn't mean that we have a reaction that is 2A plus B. And this again goes back to the fact that the only way that we can derive a rate expression and the only way that we can find out how the individual species affect the rate and by how much is through experimental evidence. It's by doing experiments and seeing how much the rate changes by when we change the concentrations. It can't be predicted from the chemical equation. Now, another example might be catalysts, which we know don't appear in the actual chemical equation, may appear in the rate expression. But if a species isn't present in the rate expression, therefore it doesn't affect the rate of reaction, we say that it is zero order with respect to that species. That has an order of reaction of 0. Now, if the rate is, so we can sort of summarise that the rate is not affected by the concentration of a species, the reaction is 0 order with respect to that species, and it's not included in the rate equation. If the rate is directly proportional to the concentration of the species, then the reaction is first order with respect to that species. So that's our example of B in the top rate expression. If I times B by 2, the rate times it by 2, so it's directly proportional to each other, and so that would be first order with respect to B. And then finally we can say that if the rate is proportional to the square of the concentration of a species, that the reaction is second order with respect to that species. So that's the A squared part in the example at the top. If I times the concentration of A by 2, because 2 squared is 4, the rate will quadruple times by 4. And so the rate is proportional to the square of the concentration, and therefore it's second order. Now, the units of the rate constant vary depending on what the overall order of the reaction is, and they must be worked out every time by cancelling units. Now, you could potentially remember these rate constants depending on what the order is. I would really strongly recommend against that, purely because you're more likely to make a mistake if you try and remember it, rather than just working it out on the spot, which is fairly easy. The key thing to remember is that the units of the rate of reaction are in mole per decimeter cubed per second, and remembering that our concentrations are always in moles per decimeter cubed. So, for example, let's first of all take a rate equation that has the form rate equals K. Very, very simple. We know that our rate is mole per decimeter cubed per second, and therefore, because there's nothing else on the right-hand side, K must have the units of moles per decimeter cubed per second. If we then go down to the bottom left, we have an expression of rate equals K concentration of A. So now we have the rate being mole per decimeter cubed per second. We have K, which we're looking to find the unit of, and we have our concentration of A, which is in moles per decimeter cubed. Now we have a mole per decimeter cubed on both sides, so we can cancel that out, and we're simply left with that K is equal to per second, seconds to the minus 1. If I have a rate law as shown on the top right, rate equals K, concentration of A, concentration of B, well, the rate, again, is in mole per decimeter cubed per second. We then have K that we're trying to find the answer to. we have our concentration of A and our concentration of B. Both of these are in units of moles per decimeter cubed. So we have moles per decimeter cubed and moles per decimeter cubed. If we have two of them, that's the same as having moles per decimeter cubed squared. So that whole mole per decimeter cubed squared. And if we use our laws of indices here, we can just times the numbers together. So mole to the 1, times by 2 is mole to the 2. Decimeter to the minus 3 times by 2 is decimeter to the minus 6. Another way to think of it is to have the mole per decimeter cubed per second on the left-hand side, the mole per decimeter cubed squared on the right-hand side, and to think of, okay, I have 1 mole per decimeter cubed on the left-hand side, 2 mole per decimeter cubes on the right-hand side, and so if I cancel 1 from either side, I'm left with just per second on the left-hand side, and k mole per decimeter cubed on the right-hand side. And so to find k, I have to divide through by mole per decimeter cubed. When we divide through by these things, the sign of the indice changes, so it becomes that k is mole to the minus 1, decimeter cubed, second to the minus 1. So if we ever have to divide through by these indices, we always have to flip the sign of what the indices are. So mole per decimeter cubed on the right-hand side, when we work out k, becomes mole to the minus 1, decimeter cubed, the positive 3, second to the minus 1. And then finally, if I have a rate law, which is k equals concentration of A squared, concentration of B, so this is a third order reaction, we have mole per decimeter cubed per second on the left-hand side, then k, and then essentially we have 3 lots of mole per decimeter cubed on the right-hand side, so mole per decimeter cubed, mole per decimeter cubed, 3 lots of them. We can then cancel out a mole per decimeter cubed on each side, or we can actually kind of expand out our brackets there and end up with mole cubed decimeter to the minus 9. Whichever way we do it, we can eventually cancel out one set of mole per decimeter cubed, and we end up with per second on the left-hand side, and the right-hand side being k mole squared decimeter to the minus 6, essentially 2 lots of mole per decimeter cubed. And then again, to find k, we now need to divide through by that mole squared decimeter to the minus 6. By dividing through by it, we have to flip the signs of our indices, and so we end up with k being mole to the minus 2, decimeter to the 6, second to the minus 1. And so I would really, really strongly encourage you to be comfortable with doing this kind of unit calculation almost, because it's much easier, I would say, and much safer to work out the units than it is to try and remember them. And so the key to doing it is simply remembering that the rate is mole per decimeter cubed per second, and concentrations are moles per decimeter cubed. So if we then come to looking at determining the rate equations, there's a couple of different experimental ways we can do it. One method of finding the order of reaction with respect to a particular species, say A, is by plotting a graph of rate against concentration. Now, in order to do this, we have to plot the graph of concentration versus time. So we plot the original graph of the concentration of A against time. That's one of the graphs we saw kind of right at the start of one of our previous videos. And so what we're going to do in order to find the rate of this, remember, if we have a concentration time graph, to find the instantaneous rate at a point, we draw tangents. And so we're going to draw tangents at different values of A, and the gradients of these tangents will be the rate of reaction at different concentrations. Now, for a zero-order reaction, we can see that our concentration time graph is a straight line, so the rate of reaction is constant. However, if we have a first or a second-order reaction, you can see that they're actually curves. And so the rate of reaction isn't constant. You can see actually that the rate of reaction, the gradient of that curve, slows down as time goes on. This is what we expect. As time goes on, we use up our reactants, therefore the collision frequency drops, and therefore our rate of reaction drops. And so we have to take multiple tangents at various different points, find the rate of reaction at different points, and then we can construct a graph of the rate against concentration. So if you're doing this in the lab, what you would do is measure the concentration of a particular, say, reactant A in this case, with time. You would then draw your tangents at various different points to calculate the rate at different times, and then plot your graph of the rate against the concentration. Now, if that rate versus concentration is a horizontal straight line, the rate is unaffected by the concentration of A, and hence the order is 0. So that first example down there on the right, we have our rate concentration graph. If it's a straight line, what that's telling you is that the rate is unaffected by the concentration of A. The rate is constant, and therefore it must be a zero order reaction. If the graph is a straight line that has a positive gradient, then we can say that the rate is proportional to the concentration of A, i.e. if I double the concentration of A, I double the rate. If I quadruple the concentration of A, I quadruple the rate. And so therefore it's proportional, and the order is 1. That's a first order. Now if we plot this rate concentration graph, and it's not a straight line, it's a curve, the order can't be found directly. What we do know though is that it's not a first or a zero order reaction. It would be a second order or higher reaction. So it could be a second order reaction. And the way to see this would be to plot the rate against concentration squared. If it's now a horizontal straight line, then the order of it is 2. So essentially, whatever you're plotting the concentration of, this idea of it is concentration squared, and it's a horizontal straight line, then the order would be 2. But the key thing is, if we get this second order sort of shape, this curve, then it's definitely not first order, it's definitely not zero order. It could be second order, could be third order. We'd have to actually replot the graph and see. So the key thing is to do it experimentally. Measure the concentration versus time, so measure the change in concentration. Take the tangent at various different points, that's the rate of reaction, change in concentration versus the change in time. And then from our tangents at lots of different times, essentially the equivalent of lots of different concentrations, we can plot a rate versus concentration graph. Now there's another type of method called the initial rate method. And the way to do this is that we're going to be using the initial rate, and we saw in a previous video that the initial rate was the rate at t equals 0. So we draw our tangent at the origin of that graph when t equals 0. Now a series of experiments are carried out at a constant temperature. Again, note that thing that we do it at a constant temperature, because of course temperature will affect the rate of reaction. Each experiment starts with a different combination of initial concentrations of the species. And the experiments are planned such that between any pair of experiments, only the concentration of one of the species is going to change. The rest of them stay the same. And for each experiment, the concentration of one reactant is followed, and we draw that concentration time graph that we saw on the left of the previous slide. And we draw our tangent to the graph at t equals 0, the start of that curve essentially. And the gradient of that tangent, the change in y over change in x, the change in concentration by the change in time, that is the initial rate. And one of the advantages of doing the initial rate method is that by using the initial rate, we know the concentrations of all substances in the reaction mixture at that time. They're known exactly. It's not like trying to measure the concentrations in the middle of a reaction where potentially we might be unsure. At the start of the reaction, we know we are definitely going to have no product, and we will definitely know how much concentration of the reactants we started with. And so then comparing the initial concentrations and the initial rates for pairs of experiments allows you to work out the order with respect to each reactant, and then overall to work out what the rate law would be. So let's have a look at an example. We have this table on the left which is showing us these different experiments, and you can see that between any pair of experiments only one concentration has changed. So for example, if we look between experiment number 1 and experiment number 2, we've kept the oxygen concentration constant at 1 times 10 to the minus 3 moles per decimeter cubed, but we've doubled the NO concentration, the nitrogen monoxide. And so by doing that, we've kept the oxygen concentration constant, therefore that's not going to have any different effect on the rate of reaction. However, we've doubled the NO concentration, so we'd look to see how the rate varied. So if we compare experiments 1 and 2, our concentration of NO has been doubled, our oxygen has been kept constant. And if we check the rate between experiments 1 and 2, the rate has increased by 4. So we know that timesing it by 2 has increased the rate by 4. So essentially we can say we have 2 to the power of the unknown, 2 to x, equals 4. And the only way this can be true is if the x equals 2, i.e. it's a NO to the power of 2. It's a squared rate law. And so we can see that there by the fact that we have double the concentration of NO and the rate has quadrupled. The only way that can happen is if it was 2 squared, timesing it by 4, and therefore its nitrogen monoxide is a second order species. If we then compare experiments 2 and 4, we can see that our oxygen has been doubled, the concentration has been doubled, but our nitrogen monoxide concentration has been kept constant. We can then compare the rates, and we can see that we've gone from 28 times 10 to the minus 4 to 56 times 10 to the minus 4, i.e. we've increased the oxygen concentration by 2, and our rate has increased by 2. And hence, because it's directly proportional, therefore it must be a first order in the rate law. We can also think about it in this kind of more mathematical sense, that it would be 2 to the x, 2 to the unknown, equals 2, and that can only be true if x equals 1, i.e. a first order with respect to oxygen. If we then look, for example, at comparing experiments 1 and 5, the example why I bring this up is because both concentrations have changed here. Typically, the way we do this is between any pair of experiments, any kind of consecutive pair of experiments, we keep a concentration constant, but between sort of various other experiment numbers, typically both concentrations will change. So between 1 and 5, you can see that both the concentration of NO and O2 has tripled. And so a good way to do this is just to double check that you've got the right orders. We know that our oxygen is first order, so if we triple the concentration, we should triple the rate, so times by 3. And we know that our NO is second order, so if we triple the concentration of NO, we should multiply the rate by 3 squared, or 9. And so if we do 9 times 3, the total increase of the rate should be 27 times. And if you see the difference between the 7 times 10 to the minus 4 and the 189 times 10 to the minus 4, that is a difference of 27. So that just proves that we've done our calculations on this correctly. And hence we can then write down our rate law. It would be that the rate is equal to K, the rate constant, NO squared, because it's second order, and oxygen to the power of 1, because it's first order. And so this is an overall third order reaction. So using the rate law that we've now determined from these experimental values, we can also find the value of our rate constant K. And the way to do this is really simple. We just have to substitute any set of values of rate and concentrations into the rate expression. And we should get the same value of K using the values for any experiment. This again is another way to double check that you've done the calculation, calculating the orders right, because if you get different answers for the rate constant using different experiments, then something must have gone wrong in calculating the orders. The key thing as well to remember is that you have to use a particular experiment number. So you can't use the NO concentration from experiment 1, the oxygen concentration from experiment 5, and the initial rate from experiment 3. It all has to be from the same experiment number. And also, once we've worked out our number, remember that we have to work out the units of the rate constant as well. So I'm going to use experiment 1. We had our rate law of rate equals K NO squared oxygen. I'm going to rearrange for K. So to do this, I have to divide by the concentrations on both sides. And so I get that K is the rate divided by the concentration of NO squared and the concentration of oxygen. Then I'm going to take my numbers from experiment 1, just plug them straight into the equation, and I end up with an answer of 7 times 10 to the 5. Then I have to work out the units. So to do this, I'm actually going to use the rearranged expression, this time of K. So K was the rate divided by the concentration, so we have our rate of mole per decimeter cubed per second. We have our concentrations, remember that they're in mole per decimeter cubed. Essentially we have 3 lots of concentration terms, so we can consider that to be mole per decimeter cubed, 3 lots of them. Then we can cancel out a mole per decimeter cubed from the top and from the bottom. This would leave us with per second on the top and mole per decimeter cubed squared on the bottom. And then, like I said earlier about sort of moving indices between top and bottom, when we do this, we have to change the sign. And so to get the mole per decimeter cubed, essentially rather than writing it as a fraction, we can write it all in one line by switching the signs of the indices. So technically we're saying that K, the unit of K, is per second divided by mole squared decimeter to the minus 6. A nicer way to write that all in one line is to say that it is mole to the minus 2 decimeter to the plus 6 per second, second to the minus 1. And so our answer is 7.0 times 10 to the 5 mole to the negative 2 decimeter to the 6 second to the minus 1. And so as we've said in previous videos, small changes in temperature produce very, very large changes in reaction rates. And so this is an inherent property of a particular reaction. And when we think about our rate constants, the larger the value of K, what that means is the faster the rate of reaction. Now K increases with temperature, and this is true for all reactions. Remember that temperature is the average kinetic energy of the particles. It's the total energy we have divided by how many particles we have. And these will only react together if they have, and they'll only collide if they have enough energy to start breaking bonds. That's when we have our successful collisions. That's our activation energy. The higher the temperature, well, the higher the percentage of molecules that have energy greater than the activation energy, and hence there are more successful collisions. If you go back to my previous video, we'll see we talk about this in more detail. That obviously at higher temperatures, more energy, the particles are moving faster, and so the collision frequency increases. But the real thing that massively increases the rate is that we now have many more particles that have energy greater than this activation energy, and hence there are lots more successful collisions. So the final thing to talk about here then is something called the rate determining step. And this is that most reactions will take place in more than one step. It very often isn't just the reactants go directly to the products. There's quite often a series of many small separate steps that lead from reactants to products. And this series of separate steps is called the reaction mechanism. Now most reactions take place in several steps. It's very, very unlikely that all of the reactant species will collide at the same time. It's much more likely that there will be sort of small groups of these reactant molecules colliding in several steps. And so the steps in between involve very short-lived intermediates. These intermediates tend to be very unstable. They are formed in one step, they get used up in the other. And these intermediates can give information about the mechanism of the reaction. But because they're so unstable, because they're so they're very, very unstable energetically, they're pretty difficult to isolate, sometimes even impossible to isolate and really identify truly. And so hence other ways of working out the mechanism must be used. Now in a multi-step reaction, the steps nearly always follow after each other. So the product of one step is the starting material for the next. Now the key thing here is that the rate of whatever the slowest step is will govern the rate of the whole process. The slowest step may form essentially kind of like a bottleneck, and this is called the rate determining or the rate limiting step. Now, a kind of sort of analogies of this maybe is if you're going home from work to your home, essentially the slowest bit of that journey is probably going to be if you get involved in a traffic jam on the motorway. It doesn't matter how quickly you've left work, how quickly you've got in your car, the slowest bit of that journey, the thing that's going to take the maximum amount of time and kind of govern the whole amount of time it takes you to get home, is being in that traffic jam. Another example might be if you're boiling the kettle for a cup of tea. The slowest bit of making the cup of tea is boiling the kettle, waiting for that to boil. So it doesn't matter really how quickly you put the water into the kettle, how quickly you put the tea bag into the cup. The rate of that process, how quickly it occurs, is going to be governed by that slowest step essentially, which is the boiling of the water in the kettle. And so this kind of bottleneck point, the slowest step, is the rate determining or the rate limiting step. Now in a chemical reaction, any step that occurs after the rate determining step will not affect the rate. That's because we've already had our slowest step. That's the thing that's really affected the rate. And so if we have steps that occur after the rate determining step that are faster than that rate determining step, they're not going to affect the rate. And so a species that are involved in the mechanism after the rate determining step, i.e. the species that are after this slowest step and they're not slower than that rate determining step, they do not appear in the rate expression because they don't affect the rate of reaction. Any species that affects the rate that is before or is the rate determining step must be included in the expression. So it could be that we have a step after our rate determining step, after the slowest step in the reaction, where one of the species affects the rate of reaction in terms of working out orders, but actually we're not going to include it in our rate equation because it's after the rate determining step. It doesn't matter, we've already had our slowest step. So when we see a rate equation, the steps that are in that rate equation and the species that are in it must have been involved before or after before or during the rate determining step. And so an example here would be this reaction between iodine and propanone, a ketone. So essentially we take propanone, we take our iodine, we take an acid catalyst, H+, and you can see essentially that we add an iodine onto the end of our ketone and we form HI. Now the actual mechanism for this I've shown here in the blue reactions here at the bottom. It's actually a 4-step mechanism. The first one is our carbonyl group acting as a base, accepting the proton. This ends up forming a carbocation. That carbocation then eliminates a proton to form an alkene. The alkene reacts with iodine, and then that iodinated species ends up losing a molecule of HI to reform the carbonyl group. Now actually, if we compare the rates of these independent steps, it is the first step that is the slowest step. That's the rate determining step. Now the rate law for this is the rate is equal to K, the concentration of the ketone, and the concentration of H+, the acid catalyst. So this is an example where we have a species that doesn't directly appear in our chemical equation, the H+ catalyst, it appears over the arrow, being included in our rate expression. We also have an example here of a species present in our chemical reaction, the iodine, that's not present in the rate equation. And this is useful for allowing us to determine which of these steps can be the rate determining step. Now the first step of this actually is the rate determining step. That first step is the slow step, the protonation of the carbonyl group. And so the key thing is that the iodine doesn't come into play until 2 steps later. The first time we see the iodine is in the 3rd step. And so this explains why iodine doesn't appear in the rate expression. Because iodine, where the iodine comes into the mechanism, occurs after the rate determining step. And remember that the species that are in our rate equation must have been either before or during the rate determining step. Hence why we see the ketone, hence why we see the H+, but we don't see the iodine. Now the order of the reaction can be used to help find the rate determining step. So let's take a pretty simple nucleophilic substitution reaction. We have bromobutane reacting with our hydroxide anion. This produces butanol, an alcohol, and kicks off the bromide anion. Now this reaction could proceed either through a 2-step mechanism where the bromine is kicked off straight away. This forms a carbocation. That's a very slow process. Then the hydroxide nucleophile, the hydroxide anion, attacks the carbocation, and that's a very fast reaction because our carbocation is positively charged, hydroxide anion is negatively charged. There's a lot of charge attraction. And this is what we call an SN1 reaction. A 1-step mechanism may also be possible, where the carbon-bromine bond and the carbon hydroxide bond are broken and made respectively at the same time. And this is what we call an SN2 reaction. Now, it depends whether your exam board wants you to know the difference between SN1 and SN2, so just double check. If you want more details on them, please check out the mechanism video that I've done on this channel. Now, there are 3 isomers of the bromobutane. We can have 1 bromobutane, 2 bromobutane, or 2-bromo, 2-methyl propane. So our 1 bromobutane and 2 bromobutane are position isomers of each other. We have the bromine either on the first carbon or on the second carbon. And the 2-bromo, 2-methyl propane is an example of a chain isomer. We've essentially changed the length of the carbon chain. We now have one of these carbon groups as a substituent rather than as part of the main chain. Now, 1 bromobutane reacts through a 2nd-order mechanism. So that is that the rate is equal to K, the bromobutane concentration, and the hydroxide anion concentration. Now, because the rate depends on both the concentration of the bromobutane and the hydroxide anions, this suggests mechanism 2, the 1-step SN2 mechanism. Because remember, only the species that are involved before or during the rate determining step, the slowest step, appear in our rate equation. Now, we said that the first mechanism here, we have our formation of the carbocation. That's very, very slow. And so because the hydroxide anion is in the 2nd step of that mechanism. And so because the hydroxide anion exists in this rate equation, it must have been either in the rate determining step or before it. That can't be possible for mechanism 1, so we have to go for mechanism 2, this SN2 reaction. The 2-bromo-2-methyl-propane actually reacts through a first-order mechanism. So the rate is equal to K, and then the concentration of the bromobutane. And this suggests mechanism 1, because remember, only the species in the rate equation are going to be the ones that affect the rate because they occur before or during the rate determining step. And so this suggests mechanism 1, where there is a slow step. The rate determining step is the breaking of the carbon-bromine bond to form the carbocation, followed by the rapid step in which the two oppositely charged ions react together. And so that CBr breaking step is the rate determining step. And so this makes sense. Our hydroxide isn't involved until the second step. And so because the first step is the rate determining, we don't see the hydroxide nucleophile in our rate equation. And so this suggests that it's actually an SN1 reaction, mechanism 1. And 2-bromobutane is a bit interesting because it actually reacts by a mixture of both mechanisms and has a much more complicated rate order, complex rate expression. So, time to have a go at some questions. So, if you'd like to have a go, pause the video and the answers will be on the next slide. So, the answers, starting with the question that was on the left, we have gases P and Q reacting together to form R and S. And we were told that we had a table here of initial concentrations and initial rates. This is an initial rate experiment that's been done, changing one of the two concentrations while keeping the other constant and seeing how the rate varies. Now, it's a slightly odd question here in that they've said gases P and Q, and then in the table they've given you G and Q. So G is the same as P in this equation. I'm going to be using P rather than G. So we have to work out the gaps in this. We were given our rate law as being equal to K, concentration of P squared, concentration of Q. So the first one to do is to work out the initial rate for experiment 2. So I'm going to compare experiments 1 and 2. Between experiments 1 and 2, the concentration of Q is unchanged, but the concentration of P has been times by 3. Now we go to our rate law. We know that P is squared. In this, it's second order with respect to P. And so we have to do 3 squared, which is 9. And so the rate is increased by 9. And if we do 5 times 10 to the minus 5 times 9, we end up with 4.5 times 10 to the minus 4. The next one along is experiment 3, which is where we don't know the concentration of Q. So I'm going to compare actually experiments 1 and 3. Between 1 and 3, our concentration of P has times by 2. Now we know that P is second order, so 2 squared is 4, so the rate's increased by 4 due to P. But if we actually look at our rate between experiments 1 and 3, you'll see that the rate has been unchanged. So while we've times the rate by 4 due to P, for it to be unchanged, we must have kind of divided the rate, if you like, by 4 because of Q. And because Q is first order, it's proportional. So to leave our rate unchanged, we need to divide our concentration by 4 to give the rate dividing by 4, which if we times it by 4 gives us no overall change. So we take our concentration of Q from the first experiment and we divide it by 4, and this gives us an answer of 4.5 times 10 to the minus 3. And the final one is experiment 4. We need to work out the initial concentration of P. I'm going to compare experiments 1 and 4 here. So the first one to note is that the concentration of Q has multiplied by 3. We know that Q is first order, and therefore the rate must have times by 3 due to Q. But actually, if we look at how the rate has changed, the rate has actually changed by 9. And so the way that I then go about this is to say, well, okay, I've got whatever P is squared, I've got the change in Q, which has been 3, and I equal that to my change in rate, which is 9. So I can then divide 3 by 3 on both sides. So we then get P squared is the same as 9 over 3, which is 3. So if P squared is equal to 3, then the change in the concentration of P must be the square root of 3. And so therefore I'm going to take, because I'm comparing experiments 1 and 4, the concentration of P from experiment 1, 2.5 times 10 to the minus 2, and then multiply it by the square root of 3. This gives us our answer as 4.3 times 10 to the minus 2. We were then asked to use the data from experiment 1 to calculate a value for the rate constant and deduce the units of k. So we have our rate law. I'm going to rearrange this for k, so divide both sides through by the concentrations. I get that k is the rate divided by p squared and q. Put the numbers in from experiment 1 and you end up with 4.4. We then have to work out our units, remember, for the rate constant for k. And so we're going to have our rate, which is mole per decimeter cubed per second. On the bottom, we have a total of 3 concentration terms, so essentially mole per decimeter cubed, 3 lots of them. So I can cancel out a mole per decimeter cubed from top and bottom. That leaves me with per second on the top and mole per decimeter cubed squared on the bottom. So that's the same as mole squared decimeter to the minus 6. And then again, rather than writing our unit as this fraction, we can all write it on one line by just changing the sign of the indices and bringing them up essentially. So we end up with our answer being 4.4 mole to the minus 2 decimeter to the 6 second to the minus 1. And the question that was on the right-hand side, we had exactly the same reaction that we've just seen, the propanone and iodine reacting in acidic conditions. We have our rate law for this as being K, the propanone, and then the H plus concentration. First of all was to give the order of this reaction. So the propanone is first order, the acid is first order, and so 1 plus 1 equals 2. The overall order is 2. We then have part C here to determine how the initial rate of reaction changes when the concentration of iodine is doubled and the concentration of propanone and HCl are unchanged. Well, we look at our rate equation. Iodine isn't in that rate equation. We saw on the previous example that the reason for that is because the rate determining step was the first step. It didn't involve iodine, and therefore, because it's after the rate determining step, it doesn't get involved in our rate expression, and so therefore the rate would be unchanged. And then finally, part D, we have the mechanism that we saw on the previous slide, and using that rate expression to suggest which of those 4 steps could be the rate determining step. The key thing is that in our rate expression, there's no iodine, so it definitely can't be step 3, and because of that, it can't be step 4 afterwards. So it has to be step 1 or 2. However, if it was step 2, we'd likely see a contribution from the alkene as well. So we probably wouldn't see a contribution from that carbocation because it gets formed in step 1, used up in step 2. But we do also form the product of this alkene in step 2. However, that's not present in our rate equation. It could be that actually that is just a 0 order with respect to that species, and that actually is the rate determining step. However, the more logical conclusion is that actually the rate determining step is the first step, because we only have the propanone and the H plus in our rate equation. So thank you for watching this video. You can find many more videos like this on my YouTube channel. If you found the video helpful, please leave a review on the tuition website. I offer online tuition for chemistry, so please check my tuition pages for prices and how to contact me. And if you need any more help with your chemistry, you can feel free to drop me an email. I'll always be happy to help.